Okay, welcome everyone to the first meeting of the OMR Compiler Architecture meeting for 2019. So today we have one topic to discuss, and it's a reorganization of the low-level memory allocator classes. And Mark Studley, who's been doing a lot of the work there, is going to take us through it. So I'll just turn it over to him.
Okay, thanks, Daryl. So I put together a set of slides to try and go through, I guess, the point of what I've been trying to do, as well as describe where I think this is going and how I'm intending to get us there. So this is sort of FYI informational and a request for feedback if people have better ideas or ideas for how to do things differently. I thought I'd start off by trying to sort of make sure I put the work that I've been considering in proper perspective, because memory allocation is it means a lot of different things in a lot of different places in OMR and OpenJ9. So I wanted to make sure I've had people's attention focused on the same areas that I'm focusing on. And basically they're the lowest areas. This slide lists kind of the sort of three levels of allocations that are happening, or three types of memory allocation that are happening in OMR and OpenJ9. So the first is the persistent allocator, which exists all the way through the entire compiler's lifetime, so it crosses different compilations. And it tends to be a very allocate and free type of style. If you don't deallocate something, it's a leak. So everything is explicitly deallocated. The second main category is I've called it region. It has been called heap or stack allocation in the past. The basic lifetime here is inside of a compilation, so it's a bunch of memory that you allocate during a compilation. We tend to allocate this using larger segments, and then smaller objects are carved out of those segments. But then the segments are typically bulk freed. It's not always the case. There are cases where objects are deallocated individually from different memory regions. But for the most part, compilation memory in this region section is bulk freed. And then the third area is the typed allocator stuff, which basically hooks all of these low-level allocators into the STL containers and allows you to do some useful lifetime management as part of the STL containers. Today, I'm primarily looking at the raw memory and segment allocation memory that are used in the first two segments here. So I will be talking about the persistent allocator a little bit, mostly at the end. And primarily, I'll be talking about the lowest level memory allocation routines that are done as part of region. I won't be talking about region itself, but I'll be talking about the allocators that provide segment memory to the region allocator fabric. There are kind of three different allocation scenarios that you need to worry about when you're thinking about memory allocation in the JIT. The first one I just called normal. It's like the usual business as usual for the JIT. It needs memory, it allocates it, and it frees it to do compilation-related work. A second scenario is kind of a debugging diagnostic scenario that we support, which not everyone knows about, but it's there. It basically changes the underlying memory allocation fabric to help you debug memory that you use after you've freed it. So that particular kind of pernicious bug, trying to figure out what is reusing this memory that you freed because you thought nobody was using it anymore. So this thing basically, rather than deallocating memory when at the point when you would normally free it, you actually change the protection access or the access protections on the memory pages to cause a fault if it gets reused, and that helps you discover these use after free scenarios. And the third one is one that OpenJ9 uses primarily, which is operating inside the debugger. So there is some compiler code in OpenJ9 which can run as part of an extension inside, say, GDB. And in that scenario, that compiler code that's running may need to allocate memory in order to perform some, it's usually to print stuff out or to operate properly. And when you're running in the debugger, you need to allocate that memory in the debugger, not in the memory of the debugee, because well, that would just be wrong. So these three scenarios are basically already supported by our memory allocation routines, and they have to be taken into account when you're in anything that changes them. So what I'm going to be proposing here, so the current implementation has a few drawbacks. I'm not actually going to describe the old implementation here. It has what I find a sort of a confusing duality between these things called segment allocators and segment providers. And there's a little bit of a lack of consistency between how OMR does things and how OpenJ9 does things, which are hampering code movement due to the dynamics of that differing code. In particular, I was trying to move the JIT builder code from OMR to make it available inside the OpenJ9 JIT, which should have been a relatively easy operation, but became very difficult because of the memory management being significantly different between the two projects. And so I set out to fix that. So what follows here is a proposal to refactor the existing code. So I'm not trying to add anything here really, although I am bringing some of the code that's in OpenJ9 down into, or up into, depending on how you move things, into OMR. I'm trying to simplify the concepts a little bit, at least in my head, and trying to avoid having classes that are really doing multiple jobs, which is one of the things that I find confusing about the current arrangement. I'm obviously trying to unify those interfaces across the two projects so that we can facilitate code movement better. Like I said, there's a couple of things that are only in OpenJ9 that OMR has extremely rudimentary implementations of that I'm trying to move into OMR so that OMR can take advantage of the improved memory efficiency that OpenJ9 exhibits. So I didn't create the complex, so this I'm going to be presenting a bunch of complex stuff, which I'm trying to simplify how to understand it. I'll do my best about that, and you'll see what I mean in a few slides. But I didn't create this complexity; it's evolved over the last 20 years. So all I'm doing is trying to find a way to explain it and structure it to make it relatively easier to understand, I hope. And what I'm trying to do here is basically do the same things that the current implementation does and make it easier to understand. So I'm not trying to change behavior. I'm hoping not to change affect performance, and obviously that will need to be tested when the ultimate change comes. Mostly I'm just moving code. All right, so having said that, let's move forward. So there are a couple of concepts that will sort of help structure the rest of the presentation. So there's when the JIT is allocating memory, there's kind of two types of memory that it allocates. One is just plain what I call raw memory, which is really just a void star. So it's kind of this is the type of memory, quote unquote, that malloc and free work with, right? It's just a blob of memory that you reference via a pointer. And this is really what the RawAllocator part of the hierarchy, which if you are already familiar with the memory allocation stuff in the compiler, or if you listen to the rest of this presentation, you'll see how RawAllocator all fits together. The second sort of concept or type of memory that gets used by the compiler is represented by a thing called tr::memory segment. So memory segment is really just a small object that represents another large separate chunk of memory, which is the actual segment. In this small object, it has a few little fields that help you track what parts of that larger segment are already being used or assigned to be used as to allocate smaller pieces of memory. So I've listed them there. You know, underscore segment is basically a pointer to the start of the memory. Underscore allocated keeps track of how many bytes you've allocated from the start of the segment. Size is the total size, and then link is used by region primarily, I think, to link different memory segments together. So memory segment is a way of taking a larger chunk of memory and basically parceling it up into smaller chunks, and you can basically do that by just handing back a pointer from taking segment and adding allocated, as long as the requested size doesn't blow the size of the full segment. And then these TR memory segments are typically bolt freed because the segment doesn't have any notion of where the internal objects are, so it doesn't have a way of individually freeing what you've done. All right, so having said that, there are then a bunch of classes that deal with the raw memory and a bunch of classes that deal with dealing with memory segments. So I'll start with the raw memory one. So the RawAllocator is a class that already exists, but I'm changing it around a little bit in this new scheme. So in particular, I'm making it an abstract class that basically represents the interface between the rest of the compiler and using raw memory. Now, for the most part, that means all the SegmentAllocator stuff, which I'll talk about in a little bit, are the ones that primarily use RawAllocator. But there are some other parts of the compiler that directly access RawAllocators, if you happen to see them. This interface for dealing with raw memory is actually quite simple. The current world has allocate and deallocate. I've added a third thing called protect, which is to support that second debug scenario of memory allocation where you want to protect the memory so that future accesses will fault. But not all raw allocators will provide a protect implementation. One of the key things about RawAllocator is that it has to be thread safe because it is used as the basis of the persistent allocation, which could be accessed by different threads. It needs to be thread safe. RawAllocator provides some convenience new and delete operators so that you can allocate memory from a RawAllocator very easily using a placement new style, as long as you make sure to press a reference to a RawAllocator object. Another interesting thing about RawAllocator is that the instances of each subclass are expected to be equivalent, which basically means you can copy RawAllocator objects willy-nilly, and you should be able to allocate memory from one RawAllocator and free it via another RawAllocator. So that means it's not keeping a list of which things it's allocated. It's really, in the simplest case, it's just a wrapper around malloc and free, right? And if you think about that, it shouldn't matter how you get to malloc or how you get to free. It should just work. So that's consistent across the subclasses. Now, it doesn't mean that you should be able to allocate with one object of one subclass and be able to free with an object of another subclass. It means within that subclass, you should be able to use different instances of the object. So the next few slides, I'll go through the various subclasses that are going to be defined. So the first one is MallocAllocator. This one actually corresponds to the current RawAllocator in the OMR compiler code base. And basically, it literally is a wrapper around malloc and free. So the allocate functions call malloc, the deallocate functions call free, and protect does nothing. So it's a very simple class. DebugAllocator is what did it get called in the original one? I can't remember. In any case, it supports the second that second scenario of memory allocation where you're trying to allocate memory that you can protect at will and then deallocate. So this doesn't end up using malloc and free under the covers. It uses a variety of different functions based on the platform. Ideally, this would be implemented by the port library, but since the current implementation doesn't use the port library, I'm not changing that at this point in time. So it has a bunch of poundif def code for different platforms, deciding whether to use mmap or virtual alloc or any of the other functions on different platforms that use to allocate memory. But this class does implement protect on most platforms. There are a couple of platforms where it doesn't know how to do it right now, but for the most part, it will try to protect the memory if it gets called, and allocate and deallocate work as you'd expect. CustomAllocator is a thing that's designed to support the debugger, that third scenario of memory allocation. So here you get to construct a RawAllocator and just tell it what function you want to use for allocate, what function you want to use for deallocate, and what function you want to use for protect. So it's a way for OpenJ9 to provide the debugger versions of malloc and free, basically, into an allocator. So it's really just a convenience wrapper that could be used for any number of different scenarios or integrations with other things, but it will be used in particular in OpenJ9 for integrating with the debugger. And that's basically it for raw memory. Sorry, I forgot. There's an OpenJ9 specific one too. So OpenJ9 uses memory allocation routines that are defined inside the OpenJ9 JVM. there's a function like J9 mem allocate memory, which is used to allocate raw memory rather than malloc. And free because OpenJ9 likes to track all of the memory that's being allocated by all of its components, not just the compiler. And so rather than use malloc and free, it uses J9 mem allocate memory and free memory, and that gets represented as a J9 memory allocator, but that's in the OpenJ9 project, just for information purposes.
So how does the J9 debug version then work?
How does the J9 debug version work? It doesn't.
So like the debug allocator with
free. Or, sorry, it uses the debug allocator, and it currently uses the debug allocator. There isn't actually I believe, I'll have to go and check this now that you've asked. The debug allocator is a thing that's provided in OMR, which means it has no idea about allocating and putting protections on J9 mem allocate, J9 memory segments. And I think that's because it's really just a diagnostic mechanism to find uses after freeze. In this scenario, you don't really care if you're tracking memory or not via J9's memory allocation routines. All right, so built on top of the raw allocators are segment allocators. So this is the class that's responsible for allocating ATR memory segment from whatever memory source it's supposed to use. Segment allocator tends to round things up into a minimum allocation size. OMR tends to use a minimum allocation size of something like 64K. OpenJ9 will use minimum allocation sizes of up to 16 megabytes, I believe, for certain segments. So basically, the segment allocator is responsible for getting a chunk of memory that's of the right size. In OMR, a segment allocator just uses a raw allocator to allocate a chunk of memory, and then it builds a TR memory object around it. In J9, J9 has a thing called a J9 memory segment, and it's the segment allocator uses that or allocates directly J9 memory segments without using a raw allocator. However, the API that it represents back up into the compiler is defined by segment allocator, so you don't have to. It's basically an abstraction over the difference between J9 memory segment and raw memory, in a way. The segment allocator, so a bare segment allocator just does allocate and deallocate straight on. If you tell it to allocate something, it will allocate memory. If you tell it to deallocate a memory, an earlier allocated segment, it will deallocate it. It has no memory, it just does whatever you tell it to do. In OpenJ9, there's a couple of caching mechanisms that are in play to try to reuse segments. Once the compiler is done with a segment, it doesn't just necessarily hand it back to the operating system, it keeps it in a list, and we'll try to reuse it over time. And so there is a thing called a segment cache in the current OMR compiler. I can't remember if it's an OMR compiler or the OpenJ9 compiler, but this is not that segment cache. This is a different type of segment cache. This segment cache is actually part of the functionality that's in, if you're familiar with the current scheme, it's the system segment provider that's doing this. Essentially, what the segment cache is doing is it's providing a way to remember segments that have already been allocated. And so it can do some carving up of things, but it only handles segments of one size to keep things simple and also to reduce fragmentation. So the model here is it's basically a delegator model. So you're always talking to the segment allocator to allocate segments, but the segment allocator will first ask the cache if it has a segment that can be reused before it will allocate anything itself. So we'll always try to use segments from the segment cache first. The segment cache itself allocates segments, which is a bit of a strange thing, I guess, or it gets segments from somewhere that it allocates, that it provides back up if it needs to. And it can actually, sorry, I know this is complicated, it's hard to explain simply, but the cache itself allocates large segments that it can carve up into smaller segments. So as an example, in OMR, I think in OpenJ9, it uses 1 megabyte segments it will allocate. but then it will carve that up into 64 kilobyte segments to hand back out to the compiler. And there's some complex ways that you can end up allocating things larger than 64 kilobytes, but still within the larger 1 megabyte segment. That I won't go into detail here. I'll just awe you with the complexity of all this stuff. But it's all hidden inside this segment cache thing. Right now, this functionality is kind of merged. They're joined together inside what does segment allocation and what does segment caching is all kind of mixed together, which makes it a little bit hard to pick apart. So I mentioned that the segment cache has to allocate segments. So how does it allocate segments? Well, it has its own segment allocator dedicated for allocating its own segments. It basically uses the new segment allocators in red. Those are different objects than the other segment allocator that's in blue on the slide. And in fact, segment caches can be chained together, so a segment cache can have another segment cache. Why do you want to do that? Well, this is the complexity of the current scenario. The compiler, you can imagine that the compiler or region, if you want, is over here on the left side of the diagram, asking the leftmost blue segment allocator for segments. It's trying to allocate segment memory. In a compilation. And so either that segment allocator will find something in a cache or it won't. There's a per compilation cache of segments. So within a compilation, that middle segment cache is trying to cache segments that are being used within this compilation. And then in OpenJ9, there's actually another segment cache which lives across all of the compilations, which really only holds on to one segment, but it's just a degenerate example of a segment cache. And this performance does actually matter. So when the original rewrite of this code or this memory allocation scheme was done, the segment cache on the right was not put in place, and performance was affected, and so we had to retrofit that back in. So this captures that in the new scheme. That you'll have a compilation segment cache as well as a longer-lived compilation segment cache. And again, it will use the same delegator model, so you delegate first to see if your downstream segment cache has a segment that you can use before you'll try to allocate anything yourself. So you might still be asking, why do we, if the segment caches can allocate segments, why do we need this first segment allocator on the left-hand side? And the reason comes down to how segments get managed by the caches. So the segment caches, as I mentioned briefly, only allocate segments of a particular size. And so if you end up having an allocation that's beyond that size, you still need some way to be able to get that segment. And so in this model, if your segment cache is allocating, say, 64 kilobyte segments, and somebody comes along and asks for 256 K of memory, you won't be able to fulfill that with a segment in the segment cache. And so you need a way to allocate. And so that's what this segment allocator is there for, really. It's only allocating large segments. And in the current scheme, if you allocate a large segment, you just hand that back. You don't try to carve it up and reuse it in the free list. If we were ever to change that, we could make this work differently. But for now, that's how this is going to work. Right. So that's the allocation scheme that sits underneath region. Then there's the persistent allocator. So persistent allocator is its own little beast. However, it kind of looks the same. Persistent allocator uses a segment allocator, and that has its own RawAllocator. So the persistent allocator allocates space for individual objects, and it maintains a free list of those objects for when they're deallocated. So we're not talking about segments now. We're talking about smaller chunks of memory that are used to allocate individual objects persistently. So the persistent allocator maintains a set of free lists to track which objects have been freed but are still obviously allocated because the backing memory segments are still allocated. And so it uses a segment allocator to allocate that backing memory, and then it portions out objects out of whichever segments it still has available. And it uses the TR memory segment to kind of figure out where the objects are, and the free list to remember internal objects within the segments. So this is a case where you're using TR memory segments, but you're not using bulk free. You're only using bulk free at the very end of the compiler when you're giving away all the memory that you've been used, because this memory is persistent. There's a mildly complicated bit here in trying to initialize the persistent allocator object at the very beginning, which resides inside the TR compiler end object, which everyone references as TR : compiler. But beyond that, this is a relatively simple thing. Okay, that's lots of stuff. And I know it wasn't a particularly exciting presentation or even particularly interesting, but I promise you the current scheme is more complicated than that. What I have a couple of more slides on here, which I'll just steamroll through them, and then we can take questions if people have questions. So what I'm doing right now is reorganizing the code into the classes that I've presented here on the previous slides. I'm going to create pull requests. In fact, there is a pull request open at OMR and one at OpenJ9 right now that have some of the changes, but an earlier version of the changes. So if you're trying to match what I've said in this presentation to what's in the current PRs at OMR or OpenJ9, forget it. You won't be able to match them up because my thinking has evolved since then, in the week since I opened them, or last changed them. So that right now what I'm doing is putting together PRs, so one PR basically per major concept. So there'll be one for all the RawAllocator stuff. There'll be one for the SegmentAllocator, one for the segment cache, so on. And what I'm going to do is contribute the code without integrating it into the rest of the project. So the code will be there, but it won't be used by anything. You'll still be using all of the old stuff. And then there'll be a plan to kind of bring the integration story, integrate those classes into the rest of the project. So I'm using OpenJ9 here as an example of a downstream component that depends on this implementation, and so it needs to participate in this reasonably complicated scheme to get things integrated. So I'm intending to keep both the old and have the new memory code active at the same time, at least for a period of time, to enable us to track down performance regressions or functional bugs. And so I'm going to use the relatively uninteresting macro name old memory as the thing that you will have to define in your downstream project if you want to retain the existing memory functionality once the new functionality is turned on in OMR. So as the example, OpenJ9, I'll do a pull request. There's actually already a pull request at OpenJ9 that will define a macro called old memory when it's building OMR. And then OMR will, the next step would be that OMR would switch after functional and performance evaluations to use the new scheme. But if, well, by default, but if old memory is defined, it will build and use the old memory allocation scheme so that OpenJ9 will continue to work the way it does today. Once that's working and we're happy with it, I'll then do the work in OpenJ9 to switch over to use the new scheme instead of the old scheme, again, after functional and performance evaluations to make sure that things are holding together. So at that point, we'll have both the old and the new memory allocators in OMR and in OpenJ9, but the old allocation code won't be used for a period of time. So I'll have some settling period, hopefully not too long. And obviously other consumers are going to be encouraged to switch to the new scheme at the same time. And then once the dust is settled and we're happy with things, then we'll tear out the old memory implementations from both OMR and OpenJ9, and we'll live on in a brave new world of new memory allocation scheme. So rough timing. I'm leaving in a week for 3 weeks, so I'll do everything before then. No. I'm hoping to create the PRs with the various classes before I leave. So I'm hoping that those will be at least created and at the project and available for people to review and see what they look like. if things go really well in the next week, I'll also try to create the integration PR so that they can see what it's going to look like once the integration is done. Some merging can happen while I'm away if it's warranted, like if the reviews go well and no more additional changes are needed from me. I find that highly unlikely, but you never know. Call me an optimist. But what I'm really expecting is for those PRs to remain open while I'm away, and they'll collect review comments, and then when I come back, I'll address the comments and we'll get them merged. And then finally, the integration PRs will obviously remain work in progress until I return. There's no way those are going to get merged until after my vacation. And then at that point, we would proceed with the rest of that integration plan in late February, which is when I come back. I'm hoping to have everything flipped over by the end of March, if that timing works out, which would maybe even mean removing the old implementations unless a downstream consumer raises their hand and yells loudly, which no one has done to date. And that's it. So I know that was a lot. Wasn't particularly greatly structured, so I'll pause for questions.
I have a question about the SegmentAllocator. You said there can be more than one instance of the SegmentAllocator.
Yes.
In your slides, you have more than one instance in slide 17 and 18. Basically, you have another SegmentAllocator when you talk about it in association with a segment cache.
Yes.
Is that primarily because the size is different at that level? Is
yes.
that when a new SegmentAllocator takes?
There's two things. So let me back up a little bit. Remember when I said that RawAllocator instances are exchangeable? You can allocate with one and free with another. You can't do that with segment allocators because the segment allocators, because they're doing both free and they have to allocate a bunch of memory and state, they keep track of which segments have been allocated so that if the segment allocator object life dies, it can free all the memory and be sure to free all the memory that it allocated. And so each of these segment allocator objects keeps track of exactly the segments that it allocated. And so it can only be used to allocate and deallocate those segments. So it's partially the size because some of those segment allocators will use different sizes, but it's also that the lifetime of those allocator objects is different, right? So on the slide, the segment cache can be changed, the slide that I'm showing, this long-lived one on the right is going to live longer than compilation, the compilations. The one in the middle is per compilation, right? And so in principle, the lifetime of the segment allocator on the left in blue and the middle one in red is similar, but they're not exactly the same. And they're also using different object sizes or different segment sizes.
So one way you could solve this is just have the long-lived one and go straight to it, right? Why have that one in the middle in a world where the sizes were the same? Can you think of a reason why?
You might be able to do that. I think it would be more confusing because at that point, the segment allocator has to be able to, when this per compilation segment cache goes away, for example, it's going to have to go deallocate, 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 and it's going to go and have to walk a bunch of lists in the segment allocator to say, okay, free this one, now look for this one, free it, now look for this one, free it. Whereas if I arrange it this way, I can just do a bulk free, just walk your list and deallocate all the segments because the lifetime is the same. Yeah. It simplifies the logic, right? And it also makes it more efficient because you don't have to search for things. You can just get rid of them all. And then there's also kind of fragmentation effects that you could also encounter if you're always freeing and deallocating and different sizes, right? It becomes more difficult to manage that memory efficiently.
Yeah, the different sizes I do get, especially since you said that it's fixed for a given segment allocator.
Right. Any other questions?
I have one other question.
Sure.
On slide 14, you say...
I don't have numbers, so I can...
Okay, anyway, it's the one that introduces SegmentAllocator.
This one?
Title, yes.
Yeah.
You say memory segment objects are allocated by the raw allocator, but actual segment memory may be allocated differently.
Yeah.
So, but,
right. I talked to that point, but didn't make it very clear that I was doing that bullet. So
there's no custom notion here, right, or none that you mentioned, at least on this slide. So
correct.
By differently, does it mean
Differently means
different way? Or?
Well, it means what it means is that the actual TR segment object is just the little object with the 4 fields in it, and then there's the actual segment memory which gets allocated differently. It may not get allocated by the raw allocator. In OMR, the segment and the TR memory segment object are both allocated using raw allocator. In J9, the TR memory segment object is allocated with the raw allocator, which means J9 mem allocate memory. The segment is a J9 memory segment, and there's a different API that you need to use to allocate that thing. And so the segment allocator helps to sort of gloss over the differences between how those segments get allocated across different projects.
So it's not so much that the API offers a way for you to pass in a way to allocate it differently. It's just allowed conceptually.
It's implemented differently, yes. Yeah. The segment allocator in OMR and the segment allocator in J9 can choose to do things in different ways, but they're still serving the same API.
Okay.
I have a question.
Sure.
When you mentioned that the segment allocator can choose to use a segment cache if it needs to, I guess the question is, if it allocates from the cache first, is there a way where it'll say I'm not gonna if the segment allocator uses the cache, is it always going to use the cache as its backing allocator, or can it decide to start allocating it with whatever it does normally? In which case, how do you know which segments came from the cache and which it itself allocated, right?
Yeah, so it could, but the way that I'm thinking to arrange this is that it will always delegate to the cache first. So the cache gets the first shot, basically, at providing a segment, and that's just so that you'll cache it first. In reality, in the current implementation, I guess is a better way to explain it. In the current implementation, the segment, the functionality that I'm calling SegmentAllocator and the segment cache are bundled together a little bit into the system segment provider class. And so the way that guy works currently is if you're allocating a quote unquote small segment, like a regular sized segment, it will try to use its free list and essentially the functionality that I'm calling the segment cache. It will try to provide a segment using the free list of segments that it's already got. But if you end up needing to allocate a large object, it will not be able to do that. And so it will go and allocate a segment, a dedicated segment for that allocation. And when that segment is returned to the system segment provider, it will just be deallocated. It won't try to cache any parts of it. And so I decided to just take those notions and separate them out so that the segment allocator will handle the big allocations and the segment cache will deal with the smaller segment sizes. And I believe this will simplify the implementation.
Okay. I guess the reason I was asking is because the segment cache that's per compilation can defer to the segment cache that's outside the compilation.
Yep.
The concern I was having was that in the current scheme, with the whole backing provider and whatnot, when the compilation ends, all memory is released except for one 16 meg segment that stays alive across compilations. Right. In this case, if the second cache defers to the long-lived cache, what logic is there so that the long-lived cache doesn't hold on to all that memory, because there could be a potential, footprint increase?
Right. So yeah. I understand the question. So the way to think about this is that the long-lived segment cache is only going to hold that one segment. Its purpose is to hold on to that one segment. So it's a special segment cache in a way. It may actually end up being, I might actually have to create a different class name for that segment cache. But the only thing that that segment cache is going to do is hold on to that one. It will allocate that first 16 megabyte segment in the beginning, and then it will hold on to it. And its only purpose is that's all it will use its segment allocator for is to deal with that 16 meg segment. And then the free list, the free segments list that's in the current system segment provider, all of the code that runs that stuff goes in the segment cache that's per compilation. And then big segments are all handled by the per compilation segment allocator.
Right. Okay. Okay, that makes more sense.
So it's really just splitting the existing implementation across these three kind of pillars of allocation.
Right. Yeah. Okay, that makes more sense because at first it just seemed.
Yeah. It looks more general than it is just because it's too hard to cover all the details in a presentation, right? So, but I just tried to introduce that there's this kind of long-lived cache, there's a per compilation cache, and then there's the per compilation segment allocation. And then the existing implementation code can be kind of split across those three divisions in a sensible way.
Right. Okay.
Hopefully.
Thanks.
Yep. Sure. Thanks, everyone.
I didn't follow all of that because some of it had to do with the old allocation scheme and some of it new. But I thought you said in amongst or what you said just now that the long-lived part of that pillar or segment cache only has one segment.
Yes.
Why is that?
Because that's what the current implementation does. In principle, there's no reason why it couldn't cache additional segments, but the way that the current system works in OpenJ9 is at the very beginning, it allocates a 16 meg segment for memory allocations, and it holds on to that segment until the end of the JVM. It gives it back at the end of each compilation, but it doesn't hand it back to the operating system or back to J9. It holds on to that segment. And it's actually arranged in a little bit of a strange way in OpenJ9 right now because what ends up being this long-lived cache actually has a pointer to the per compilation object, the system segment provider thing. And so what ends up happening is the system segment provider object dies on every compilation, but this cache has a pointer to it that goes dangly at the end of the compilation, and then it gets kind of recreated at the beginning of compilation. And that functionality is just being used to hold on to that one segment. So I decided I kind of changed the ordering here so that you only have shorter-lived objects have pointers to older-lived things, but not the other way around. So there's no dangling pointers in this scenario anymore.
So Vijay, to give you motivation as to why that 16 meg segment was even there in the first place was because apparently if you don't keep a 16 meg segment between compilations, there'd be a regression because of the overhead of calling the OS to allocate memory. But if you held on to too much, then you would see footprint regressions because it would show up in your RSS. So this is sort of the trade-off that Luke came up with.
Okay, so it's not like it's a requirement. I mean, you could do more, but it's just the sweet spot that was found at the time.
Correct.
Yeah, more of it.
You said that this segment is not released until the very end of the JVM?
It's not released until, so it's allocated, I think, in process entries.
Okay,
so when process entries stops.
So that means there is no compilation in progress.
Right.
We will free it.
Yeah.
We free it after, in J9, it frees it after 256 milliseconds of no compilation.
Actually, the way I know it is each compilation thread has a such segment.
It does. Each one has its own segment, but because there are multiple threads that can process the entry,
right.
When one thread quits its loop, it frees it.
Yeah, that's a good point. So the long-lived guy, there's one per thread.
One per thread, and it disappears when the compilation goes to sleep. Because there is no work.
Yeah. So,
No, I know that for a fact. Because I would be surprised if I see stretch segments and there's nothing going on in those.
Fair enough. Yes. Yeah.
Any more questions for Mark?
I have a question. So with the current APIs as you've imagined them, what you've shown in this slide is what OpenJ9 will do. But would it be possible then for...
In fact, OMR will do this too. It may not, actually OMR may not have the long-lived guy because he doesn't have, OMR doesn't have the similar code that OMR, that code is in OpenJ9, it's not in OMR.
Right.
But the left two of these will be in OMR.
Okay, that makes sense.
Even though they're not right now. So the segment, right now the segment cache doesn't exist in OMR.
Right.
And also the persistent allocator doesn't exist in OMR right now.
Right.
But it does, but it's a very thin wrapper around RawAllocator.
Yeah, okay. So would it be possible then for a downstream project to also re-architect their own version of chaining of caches?
I don't see why not.
Okay. And then would it be possible just...
So, sorry, just let me just elaborate on that a little bit. So, SegmentAllocator, I believe, I haven't actually decided for sure that SegmentAllocator will be extensible, but segment cache will probably be extensible. So that would provide mechanisms for downstream projects to do what they'd like.
And would it be possible just with the APIs to say, have the segment allocator on the first segment cache also have a segment cache?
I don't see why not.
Okay.
The only difference between those two segment allocators is really the constructor arguments that are passed to it, as well as whether or not it has passed a cache.
Okay, great.
So the segment allocator decides whether or not to delegate to a cache based on whether it was constructed and told to have a cache.
Right, okay.
Yeah. So arbitrary complexity is probably possible.
Okay.
Possibly not warranted.
That answers my question.
Okay. Any more discussion on this?
So welcome, I guess that's the last point. I'll welcome any feedback on the pull requests as they get opened or issues that are there. So if you have further thoughts on this, feel free to reach out in the issue, or you can ask questions on the Slack, or even send me an email if you want. But Slack or the issues are probably or pull requests are probably the best places to reach out.
So when we mentioned chaining caches, was that not by having one allocator that is caching with one size, and then it's backing allocator caches with a different size? Or was there a different relationship going on there?
You mean?
I haven't been able to see the slides. I'm not connected to network.
Sorry. Looks like that.
Okay.
So basically, allocations come in on the segment allocator. The segment allocator will first say, "Hey, I have a request for X bytes. I have a segment cache. Can the segment cache give me a segment?" If it can't, then it will allocate it itself. If it can, it will return the segment that returns by the segment cache. Then the segment cache can also have a downstream segment cache, which it should ask first if it can get that segment.
Okay.
And then, as Leonardo says, you could, in principle, chain these in arbitrarily complex and scary ways. But this represents basically what OpenJ9 does today. If in not great detail. And so the thing that's not described here are the rules that whereby the code decides to go in this cache or that cache, or this allocator or this cache. Right. But in principle, it's like at a very high level, it's delegate to the cache. If the cache can serve the request, then use that, because the theory is the cache has already allocated that memory. If it has it available, I should use it rather than allocate new memory.
Right.
It's only if I don't have an existing segment that I've already allocated and holding on to that can serve that.
And the blue RawAllocator there is only for the large things that shouldn't touch the cache.
Correct.
Okay.
Correct.
I'll post your slides somewhere so that.
Thanks.
I think I can it to the agenda issue.
Mm-hmm. Cool.
Okay. There's no other discussion. Thank you, Mark, for taking us through that.
Problem.
And that's our last topic. So we'll adjourn for this week. Thanks, everyone, for joining. Bye.